So we're doing 6 of these seminars overseas, and then a kind of summation back in Oxford in September. They're all on either big ideas or big issues, which will take us through the 21st century. We thought we'd better limit our ambition to 75 years rather than the next 750 years. So that's the broad aim. And tonight's, of course, is on one of the biggest and most contentious, I suppose, issues which face us, climate change and the energy requirements for the 21st century. We're filming, as you can see, all of these seminars, and we're going to load them up onto an intranet, which will be open to Balliol alumni, but also to distinguished guests. And we hope that the debate will then be carried on the intranet, and all 6 of these overseas discussions will be available. So I just give you there's maybe even an element of warning attached to that what you say in the discussion might actually end up in at least a semi-public domain. Format of the discussion is quite simple. We're going to have 3 20-minute presentations. I'll invite people to ask sort of factual questions of each presentation after the presentation is finished. We might just have a very short session at that point, 5 minutes, 10 minutes on each one. After the presentations, we'll have a short pause to allow ourselves to go for a walk or whatever we do in short pauses, and then we'll have a general discussion. So that's the idea, and then I hope you'll join us for some refreshments at the end of the evening. I'm going to thank Dr. Charles Tannock at this point, because he's our host here this evening, and we're very, very grateful, Charles, for you putting this together for us. And one last word before I introduce our speakers, just to calm the nerves of my development director, Judy Longworth, who sits 2 places along from me here. I will say something about the 750th appeal and Balliol fundraising at the end of the meeting, but I think we should roll with the serious intellectual stuff before I hold out my hand. So we've got 3 speakers this evening. Professor Gideon Henderson, who's actually from University College. Some of you will know that we had hope that a Balliol man, an Eastman professor, would be talking this evening, but unfortunately he's ill, and so Gideon has very, very generously stepped in more or less at the last minute. So Gideon, we are very, very grateful. Gideon's professor at the university. Dermot O'Hare, my vice master, though he won't like the personal pronoun there, but professor of chemistry at the university will follow. Gideon's going to be doing the climate change scene setting. Dermot's going to be talking about fuel and sustainability and carbon dioxide. And then Dr. William Barfoot, also from Balliol, who's going to be talking about electricity from sunlight, insights from chemistry and physics. So that's the lineup. And I think, Gideon, I could just pass over to you.
Okay, thanks very much for the introduction. I'll try very hard to fill Carl Wunsch's shoes, who I'm here to replace, and he's a giant of the field, so it's a difficult job to step into, but hopefully I can live up to it. I should also say, I don't think I've given a lecture in quite this format before. It's strange for me to be sitting down with my PowerPoint up on one side like this. I hope it works, and I hope you don't crick your necks looking at it. But I'm going to talk about climate change, and I'm going to talk about the history of climate change. And we often hear, when we talk about history of mankind and humankind, that we can use history to inform us about current situations. If we're interested in conflict or a political situation, we often think about the role that history has to teach us how we can predict something about the future and how our actions will play out. So one of the things that I want to convince you about in the next 15 or 20 minutes is that the same is also true of climate, and we can use the history of climate on this planet to inform us about how we expect climate to change in the future and how our actions now will play out in future years. That's what I'm going to do. But before I start talking about some of my own research in climate change, I think the nature of working in this field, in climate change, which is so controversial, is that often, despite the overwhelming evidence that says that climate change is being caused by human activity, it's still often seen as an active debate. So I wanted to say a few words at the beginning about some of my own personal reasons why I so strongly believe that climate change is being driven by human activity. And each scientist that you ask would probably give a different version of their favourite couple of bits of evidence. So this is not a universal statement, but it'll give you some idea of why I personally feel strongly that this is a real phenomenon. So to start that explanation, I think if I was reading a textbook to advise me about talking to an audience that contains some non-scientists, one of the things that it would say very clearly is whatever you do, don't show an equation. So this is not recommended practice for a talk like this one at all. I'm going to start with an equation because I think it's such a fundamental equation to explain what's going on the Earth. And I'll try and talk you through it. There's not many things in there, so I can walk you through it. Fs here is the flux from the sun. It's the amount of energy that shines on the sun, which we can measure. This thing, alpha, stands for albedo. It's how reflective the planet is and how much of the energy that arrives is reflected back to space again. And this left-hand side of the equation I've written here tells you about the energy that's arriving on the planet. This is the energy from the sun that we are being bathed in. Now, this is a balanced system. That energy in must be balanced by energy going out again. And that's the other side of the equation here. The sigma here is a physical constant, the Stefan-Boltzmann constant. And like albedo and solar energy, we can measure the constant very well. So we can measure all the terms in this expression apart from T, which is temperature. And therefore, we can use this piece of physics to predict for us the temperature of a planet. Any planet we can use this for, and that includes Earth. And when we do that, when we run through this calculation using our careful observations and measurements, what we do is predict a temperature for the planet of minus 15 degrees centigrade. So the planet should look like this. We should have frozen oceans. The planet should not be anything like the plus 15 that we see today. There's nothing wrong with the equation that I showed you before. It's solid physics. We understand it well. The problem is that there's something missing in that equation. And the thing that's missing in that equation is the greenhouse effect. It's the fact that the atmosphere on our planet traps heat on the surface of the planet. And it's the top of the atmosphere that radiates at minus 15. And underneath that atmosphere, we're at plus 15, warmed by our atmosphere. And I can explain that if I break another rule of presentational skills when talking to a non-expert audience. The second rule, apart from not showing an equation, is whatever you do, don't show complicated graphs. So this one is also not something I should be showing.
It's not
But,
complicated.
okay, I'm told it's not complicated. That's okay. I'm all right. So this graph shows some black body curves. And for those of you who can remember your high school or university science, that's a phrase that you might be familiar with. Everything emits energy. I am, table is, the lights are. Everything emits energy. And the spectrum of that energy that's emitted depends on the temperature of that body. So this is a figure that shows those sorts of spectra. This is the amount of energy on this axis against the wavelength here. And you can see various black body curves in the dashed lines for different temperatures on here, with the one in red that I've highlighted being for 7 degrees centigrade. Now, the Earth at plus 15 should be emitting slightly above that red curve, according to black body theory. What we see in the black here is the actual line of emission as measured outside of the Earth's atmosphere from a satellite of what is being emitted. And what you can see is that for some parts of the spectrum, the Earth is indeed emitting according to the theoretical black body curve. But in other parts of the spectrum, quite large chunks of the spectrum, in fact, we find that there's energy missing, and that energy is being trapped by gases in the atmosphere. And you see on this figure, those gases are labelled water, carbon dioxide, and methane. And those greenhouse gases are what cause the Earth to be 30 degrees warmer than we would think from that simple physical explanation, that physical equation that I showed you at the beginning. So here we have some very simple physics showing us what we would expect the temperature to be and explaining why it's actually 30 degrees warmer than we might expect otherwise. So what are we doing to this climate system? Well, if we look at a figure of the carbon dioxide levels in our atmosphere here, plotted for the last 10,000 years. So here we see one example of how we can use the past to gain information. You can see that ice core records show us that CO2 has not changed very much during the last 10,000 years, but in the last 50 to 100 years, it's shot up. And more recently, it's obviously actual measurements rather than ice core reconstructions. So we're effectively running an enormous experiment on our planet. We know that CO2 is keeping us warm. We know it's a greenhouse gas, and we're pouring loads and loads of it into our atmosphere, and we would expect, therefore, according to that physics, that the planet should get warmer. And that is actually exactly what's going on. This is an experiment that's working. We're trying to warm the planet, and we seem to be managing to do it.
I am somewhat at a loss to understand why, before the era of 4x4s, you think the CO2 was changing in a cyclical way and driving climate.
Well, this would be a fascinating tutorial. I need at least an hour to deal with those questions. Possibly, in fact, I need a whole 4-year undergraduate course to deal with that lot. The changes that you see through 600,000 or 700,000 years, superimposed with this arrow, is the current CO2 levels up here. So you can see the change of CO2 that we've imposed by our warming, and that's happened in something like 50 years. Whereas the change of CO2 that you see coming out of an ice age takes something like 6,000 years. I was in particular using past climates to justify our belief that the climate is warming as a consequence of human activity. We can see clear evidence from some paleo records that this is what we would expect to happen in the future, and it's already happening now. As we release CO2, that's going to cause significant global warming. I went on in my talk, and what I was demonstrating was some of my own research, looking at the melting of the permafrost in warm times in the past and using that to understand what's going to happen to permafrost in the future, and demonstrating we expect to see significant carbon release from permafrost if we go above 1.5 degrees of warming.
When you capture carbon dioxide, I'll talk a little bit about that in my next 2 or 3 slides. There's several things you might consider doing with it in a kind of general sort of brainstorming way. You can either convert it or just use it as it comes. And so as a chemist, I'm going to propose it. This is quite a good thing to do. Of course, there are solutions involving carbon dioxide where you don't convert it into anything. You just stick it down a big hole in the ground and forget about it. Well, of course, you might think I'm a bit skeptical about that, which is true, but it is, possible. And we can also think of things to do with carbon dioxide that don't require converting it, which I'm just going to give you 1 or 2 slides just to sort of give you a neutral view here. So if you think about storage and non-conversion strategies, Gideon's probably more expert in this than me, but there are well-argued now theses on this where you can, obviously the ocean, as we have talked about, is a dominant store here. There's numbers you won't see which are in the gigatons. Down deep saline deposits is also possible, and also combining it to use, this is called enhanced oil recovery. A lot of American companies and elsewhere are using this now. You pressurize your oil reserve, and that pushes more oil out. So it's a way of recovering the last, or making the oil wells more efficient in terms of delivering the last traces of oil. So these are ongoing and will be part of a large solution. Generally, carbon capture and storage, from what I can gather, the top one, this is activity in this field, which I got from a recent review. The US here dominates. There are quite a large number of now pilot studies where they're going into major carbon capture and storage systems. To do that, of course, this strategy, first of all, requires you to separate carbon dioxide in a pure form. So there's some kind of membrane technology or something you're going to have to develop here to separate it from other gases. It then has to be liquefied and then stored in some long-term reservoir. Power plants now, of course, under certain conditions, are quite good sources of carbon dioxide in terms of its purity and so on. And now quite a lot, I think all major power stations now are going to be equipped with carbon capture technologies. I'm not talking about that tonight, but there are many strategies. That's only a temporary, because it uses chemistry to do it, and it can't can only be a short-term storage. You've got to then find a way of then capturing it and then using it. So carbon capture in itself is no good because it's captured by another compound. Where does that compound come from? You've got to make it. It's only a temporary capture and then it somehow locking it away in a mineralization system. But you have to think about the whole cycle because permanent capture of carbon dioxide can cost you a lot more energy. Where does your energy come from? Burning fuel. So it's not an easy solution. And there are debates about whether it's permanent anyway and whether we have sufficient storage. So there's issues about permanency and diffusion and it coming back up into our climate, or actually whether it's actually technically feasible and where are we going to do it. And moving carbon dioxide around is notoriously difficult. So I'm a chemist, and what are chemists going to do? So we've captured carbon dioxide. That can be a transient capture and a recycle. That can be a membrane system, and of course you could store it. But that box says fuels and feedstocks. So I would actually propose that we should use it in chemistry. Make it become a major building block in the chemical world. So I'm going to propose that we now think about carbon dioxide more and more critically as a reagent that we can then change and get our chemistry toolbox out and make useful things. So you can do several things. You can make it into more complicated structures. Of course, plants are quite good at that. And that's not what I'm going to talk about. I'm not talking about photosynthesis or artificial photosynthesis. I would actually quite like to convert it into fuel. Now, there are many different kinds of fuel, and I'll have a few slides on that. But that seems to me a kind of double win, a win-win, in that you capture carbon dioxide and you make something that's useful. And we'll elaborate a bit more on how that might work in a minute.
Are you saying that this could be, methanol could be the diesel of the future with enough energy density per cubic meter to actually run a lorry, and then it'd be effectively carbon neutral? You'd have presumably nuclear power and renewables making the hydrogen from water, and then this would be used as your fuel replacement.
Yeah, I mean, if you could make renewably diesel or gasoline, we have no problems. It's the problem about added value. At the minute, the price of hydrogen is worth more than methanol. So, you talk to BASF or the ExxonMobil or so on, and they do the sums and they say, where's your hydrogen going to come from? And I say that, they say, but that's going to cost us a lot of money. Of course, because there's no, and we were talking in the car on the way, there's no credit yet for taking the CO2. Therefore, they just look at the numbers. So therefore, they're not going to invest $1 million into my lab just on a whim, because they can't ever see, even if my process worked, they can't see how they can make money out of it. In 5 years. Everything's 5 years. I talked about carbon dioxide and I talked about fuel and how they're interrelated. And as a chemist, I introduced the audience to the sort of cutting edge conversion technologies that now are emerging on how to convert carbon dioxide into useful chemicals, which I think is one of the new frontiers that we need to get to grips with.
To William Barford, who's now going to talk about electricity from sunlight and insights from chemistry and physics this time.
Yes, thank you, Master. Now I want to move on to discuss how we can harvest sunlight to form energy, and the three main kinds of harvesting of sunlight. The first is, of course, the biological method of photosynthesis. It's been around for 2 or 3 billion years. Photosynthesis is the conversion of light and water and carbon dioxide to form carbohydrates and oxygen. But that actually is a very inefficient process. So it turns out that leaves have efficiency of about 5% of conversion of solar energy to chemical energy. So very low efficiency, in fact. And moreover, that's only converting one energy into another type of energy, namely solar energy to chemical energy. That must then be burnt or combusted to make mechanical work. So in practice, the amount of energy you get out from plants is roughly 1% of solar energy which they receive from sunlight. So that tells me immediately that we can't imagine planting Britain with crops and harvesting it. That only gives us that would only give us the amount of energy we receive from the sun by 1%. That would equal our total energy usages, but clearly that's not going to be a feasible and practical solution to solve energy problems in practice. The second kind of way of getting energy from the sun is, I want to make this point here, that by burning fossil fuels, we are basically releasing solar energy and carbon dioxide, which has been stored for over 300 million years. So in the Carboniferous period, we used photosynthesis, or plant used photosynthesis to store energy in the planet, and we're now burning this energy up at great rates. So we had to find some way, I believe, to power our planet. So the second way we can, in principle, convert sunlight into energy is via heat. And this graph, this picture here shows essentially heating up water, both in domestic plants and also in power stations at very high temperatures, to power conventional turbines and create electricity from essentially heating up water, creating steam, and then creating electricity. And the final way of making electricity from sunlight is photovoltaic devices. That's shown here. So here I show a semiconductor which absorbs light, that creates what's called an excitation, electron-hole pair, which then converts solar energy into electrical work. And that'll be my main focus, the remaining part of this talk. So a bit about conventional devices and efficiencies. So conventionally, you see a lot around silicon devices. Silicon is a very efficient way of converting sunlight to electricity, and unfortunately, this panel is not shown up very well here, but the conversion of sunlight into energy from a crystalline solar cell is roughly 25%. So in fact, actually very good efficiency. Amorphous silicon has much lower efficiency of roughly 10%, and gallium arsenide has also quite a high efficiency of roughly 25%. Now, there's one problem in converting light into electricity, and there's a fundamental limit on the conversion of solar energy into electrical power called the Shockley-Queisser limit. I'll briefly mention that in a second, explain where that comes from. It's a thermodynamic constraint on converting light energy into electrical energy. And the constraint occurs in the following way. As we heard from Gideon already, we know about black body radiators. The sun is a black body radiator. And this graph here shows the intensity of light received from the sun on the planet's surface. So the sun has a temperature of roughly 5,000 degrees Celsius. And so this is a black body spectrum of light received from the Earth from the sun. The red part here is the light received on the Earth's surface in going through the atmosphere. And these parts here are where the molecules in the atmosphere, water, carbon dioxide, absorb energy, and they prevent some of the infrared light reaching the Earth's surface. But the point is this, that the sun emits energy, light at all wavelengths, whereas solar cells absorb only at certain given wavelengths. And that constraint then determines the maximum efficiency of a solar cell, called the Shockley-Queisser limit. It turns out that this graph here shows the efficiency of a device functioning what's called the energy band gap. And silicon is the Goldilocks device, whereby it has a maximum efficiency of roughly 30% in practice, in principle, if it was operating with proper efficiency. Unfortunately, silicon also has additional losses, which means that in practice, it's roughly 25% efficient. But all other devices are either more or less efficient than silicon. And so it's a fundamental constraint on the efficiency of a device. It must be less than 30% for a single junction device. Now, this table here shows the new generation of photovoltaic devices. And there are three kinds I want to discuss very briefly. There's one kind called the multi-junction device, which breaks the Shockley-Queisser limit, has a theoretical limit of roughly 66% of efficiency. The second device I want to mention are organic devices, and the third are what are called dye-sensitized devices. So a multi-junction device works in the following way. It absorbs light over the entire spectrum. So it has this three different kinds of semiconductor which absorb light. Has a what's called a high band gap, middle band gap, and low band gap semiconductor. And the high band gap semiconductor absorbs the blue light in the solar spectrum. It then lets through the green and the red light. And the mid band gap semiconductor then absorbs the green light. And finally, the low band gap absorbs the red light. So by doing this, we absorb much more of the solar spectrum and achieve higher efficiencies. And the current best value is roughly 38% for this kind of so-called three-junction device. Now, nature has already harnessed this principle in leaves. Leaves contain pigments that absorb light. And there are two kinds. So there's chlorophylls and these long-chain molecules called carotenoids. These diagrams here show you the chemical structure where the carbon atom is the main element in the molecular structure, and the lines here are bonds between different carbon atoms. Now, chlorophyll absorbs light in the purple and orange part of the spectrum, and hence transmits green light. So that's why it's green in leaves, whereas carotenoids absorb in the green-blue part of the spectrum and hence look orange. And in fact, leaves in the autumn, what happens in the leaves in autumn is they first start to decompose the chlorophyll molecules, and they leave behind some carotenoid molecules, hence they turn brown in the autumn. That's the main chemical reason why leaves turn brown in autumn. We decompose first chlorophylls, leaving behind these long-chain carotenoids, which then look orangey or browny in light. Now, this slide also helps me to introduce the idea of organic systems. Now, chemists are very versatile in devising very, very complex organic molecules based on carbon. Carbon is a very, very useful atom. It bonds with many other elements. It has 4 valence electrons that forms very complex molecular structures, including what's shown here are long-chain polymers, and also what are called here Buckminster fullerenes. A Buckminster fullerene is a C60 molecule with 60 carbon atoms, which looks like a bit like a football in its structure. These organic devices then are, as I'll show in a second, are both cheap to make and easy to process. And in this device, what happens is the polymers absorb photons, absorb light. They then transport this excitation to a junction between the polymer and the carbon buckyball, which then splits the electron hole pair, and then electrons flow through the Buckminster fullerene part of the blend, and holes flow through the polymer part of the blend. And here I show some work done by a collaborator in Sheffield, where, in fact, they can spray coat large areas of systems by these polymer devices. These polymers are solution processable, hence they can be spray coated over very large areas, and hence the principle can lead us to have very cheap and reasonably efficient devices. Unfortunately, they're not very efficient. They're about 5% efficient because of various losses which take part in these devices. So currently, the best efficiency is roughly 5 to 10% in these polymer or plastic devices. And my own research, which I want to just briefly mention, is a theoretical understanding of what happens in these devices. And one of the key losses is that when the polymers absorb light, what happens next is this excitation, electron hole pair, must be transported to a junction between a polymer and a buckyball, and then we must then split the electron hole pair to form the current of holes and electrons. But unfortunately, what happens is the electron hole pair re-radiates very rapidly and never reaches this junction, so we can't harness the entire energy of light instant on these plastic devices. So currently, there's a lot of research going on in my group and elsewhere in understanding the role of morphology and conformation in determining electronic properties of plastic devices. And finally, the third kind of device, or called dye-sensitized solar cells. These are titanium oxide nanoparticles, so particles roughly 1,000 millionths of a millimeter in size, which have some pigment coating on them, which absorbs the light. Light then creates an electron hole pair, which then split at the boundary of the pigment and titanium oxide nanoparticle, and in fact the electrons go through the nanoparticles and the holes go through electrolytes, and again that creates electric current. And in Oxford, there's a group in physics headed up by Henry Snaith, who I think you can just see here, peering through a glass panel, which is formed by coating a glass panel by these sensitized solar cells. And again, the good thing about these is that they can be used to create very large area devices cheaply, and relatively efficiency, about 10% efficiency, is the current maximum efficiency of those devices. So, in conclusion, I want to make some concluding remarks. The first is that solar cells can make a contribution to energy production in the UK, but it can't solve our energy crisis. So we have to find other ways of making energy to solve the gap which will be left eventually when the fossil fuels run out. And there are challenges in this area in making cheap and efficient devices, which is ongoing research. And chemists can make contributions, both synthesizing complex organic molecules, but also in understanding the basic properties of absorbing light and how those molecules then conduct electricity to make electrical power in practice. So that's all I want to say on that. Thank you.
And so once again, are there any specific observations or questions or thoughts? Sorry. Beg your pardon.
Yeah, just on that last point, just a simple question. When you talk about the challenges remaining, it's said that if the Chinese were to focus on the issue of producing these kinds of devices with their massive resources and their brain power and so on, that you could see very rapid advance. But do you think that these challenges are challenges of science, or are they sort of industrial challenges?
Currently they're both, so it's both the science and industrial scale-up of these devices. There's no more brain power in China than in other parts of the world, actually, so that's not really an issue, I don't think. So I tried to explain there are these fundamental limits on efficiency devices of roughly 30%. So no device will ever get roughly much more than that. And bearing in mind how much energy we receive from the sun, we can't harness all the sun's energy efficiently to use that as a means of solving our energy crisis. So there are science issues. So I'd go back to the plastic devices here. Science issues are the fact, as I say, when these polymers absorb light, the light then creates an excitation which must then reach a junction to form electrical power. And that's a hard problem because in practice, this light excitation re-radiates back into the environment. And so we don't yet know how to solve that problem. So my own research is trying to understand how these, what are called electron hole pairs, diffuse from the polymer to the polymer carbon buckyball junction. So that requires brain power, but it also, my own feeling is that's a scientific problem which can't be solved because of the fact that when one processes these devices, they're uncontrolled processing systems. So what happens is they have polymers and buckyballs in some solution, and it's a very uncontrolled process in making a morphology and conformation, which then determines those electrical processes. And so if we can try to understand better the role of morphology, that's the structure of the polymers, and conformation, that's also the structure, determining electronic processes, then maybe we can then predict which chemicals and what structures will give us better efficiencies. But there's no magic wand here. There are difficulties in my opinion, in using sunlight to get energy, and well, it's interesting that nature doesn't do very well itself. So nature has had a long time to evolve photosynthetic devices, and namely leaves, and has a very low efficiency. So you may argue it's because it didn't have to evolve anything better. That's to say very efficient, it hasn't evolved because it didn't have to do that. Or maybe there are some fundamental constraints on the way in which chemicals, their structure and so forth, allow us to absorb light and then convert that to some electrical energy.
Speaking more of the politician, this summer I was sort of touring through Spain and I saw whole fields now,
Yes.
which would have presumably traditionally been used for agricultural purposes, full of solar panels, silicon type.
Yes.
And obviously local farmers were deciding it was probably more lucrative to make electricity from their fields than plant grapes or crops or whatever. But also the European Union is very active in financing a project called Desertec in North Africa, in desert areas, to have huge batteries of solar panels and then export the electricity to our markets. But I don't really have a feel in terms of size. Perhaps, you know, once you've overcome the technology and the science, and if you can have large areas, even with very low efficiency yields, and you could say spray or put these panels onto your household domestic windows or roofs rather than small panels, would it be possible, theoretically at least, even with a sort of 5% yield in a sort of English winter day, as it were, to say accumulate enough electricity during the day to say fuel the household needs at night, you know, sort of ordinary household power in a battery system, or would you still need to plug into the grid at night to watch your television and power up your computer?
Yes, that's a good question. So I'm not really familiar with how to store energy. That's something which Dermot briefly mentioned. So during the day, of course, the house would be absorbing light and no one's around the house during the day, so we have to then put that energy back into the national grid. So one key challenge then is to learn how to store energy better and more efficiently. There was an interesting article in yesterday's Sunday Times, which was of interest to me. In Peterborough, they wish to build a 900-acre solar farm, which actually would power 91 megawatts power. 91 megawatts is rough energy consumption of Oxford. So a 900-acre farm is roughly 1 square mile in size, and that's big enough to power a town city the size of Oxford. But sadly, the farmers, as you say, so it's valuable farming land, and so they're opposed to that, as is a local MP who is fighting the Peterborough County Council's wish to build this large solar farm. So there are those spin-offs. You can't, if you want to cover the country with solar panels, then you can't grow crops. But remember that growing crops is only about 1% efficient. Solar farms are about 25 to 30% efficient. So it's more efficient to actually make electricity from sunlight than it is to grow crops.
Do you think that these challenges are challenges of science, or are they sort of industrial challenges?
There are these fundamental limits on efficiency devices of roughly 30%. So no device will ever get roughly much more than that. And bearing in mind how much energy we receive from the sun, we can't harness all the sun's energy efficiently to use that as a means of solving energy crisis. My takeaway on today's discussion is there are still skeptics around who don't believe in climate change, and that worries me for various reasons, because I think we need to make some big decisions about solving these problems. And so I am worried that we have people in authority in Parliament and so forth who don't seem to accept the science.
It was very nice to see the sort of political angle to it, and they could see that maybe industry may not be the best way of funding this work. Maybe it's going to be politically driven, or put a price on carbon dioxide. At the minute, there's no effective price, so the companies don't need to remove CO2. If that became a real cost to them, then the economics of my chemistry would change dramatically.
I think this is a sort of Oxford flavour to the evening, that we brought so many different ideas to the table, interdisciplinary ideas that brought in the chemistry and the physics, and then the social and the geopolitical thinking. And to have it in the European Parliament building was also wonderful in its sort of a cross-nation setting.